Now we're going to talk about a different type of motion than what we've talked about so far. We've talked so far about moving in the x, the y, and the z directions, and now we want to ask if we can describe motion in a rotational way. Objects are spinning like wheels, etc. So that's the subject of this chapter. Lots of applications. The simplest kind of rotation is one where we have an object that rotates and that points on the object rotate in circular paths around some axis of rotation. We're going to use the word rigid body rotation a lot. And so a rigid body rotation means that if you're a skater, then you're going to hold your shape as you rotate. All parts of your body are rotating at the same rate, rather than moving around as you rotate. So let's define the angular displacement for rigid body rotation. The angular displacement of a point on a rotating rigid body is the change in its angular position. You have seen that language before. If you just remove the word angular, then what we called the displacement vector was the change in the position r. Here, the displacement is going to be the change in angular position. The angular position is measured by an angle theta. It's normally measured counterclockwise from some axis, some reference line. And so we're thinking about the CD spinning here and asking about the angular position and displacement of some particular point on that CD. So let's look at this point on the rim of the CD and make a little red mark with a marker on the edge of the CD. Initially, the angular position, theta, it's called theta naught for initial. So this will be our initial position. That's an I if you can't read it. And this is our final position of that point on the rim of the CD. And the angular displacement, delta theta, is the final angular position minus the initial angular position. So this is delta theta. Delta means final minus initial in the usual way. It's the final position, theta, minus the initial angular position, theta naught. We normally measure angular positions and displacements in radians, where there are 2 pi radians in one circle. Sometimes, though, we'll measure angular positions and velocity, angular positions and displacements in degrees. And so for a complete circle going around the whole circle is 2 pi radians, and that's equal to 360 degrees. That's a conversion factor, and you'll use that. You can make that into a conversion factor by just dividing both sides by 360, for example. You get 2 pi radians for 360 degrees, and that will be a conversion factor, or you can flip it over to convert radians to degrees. And all of your calculators, of course, will do either radians or degrees. Another important point, we talked about measuring theta counterclockwise. So if you think about an x and y axis, normally the way that angles are measured are counterclockwise from the x-axis. An angular displacement that moves, instead of, this is counterclockwise, but instead of counterclockwise, if we go clockwise, then those angular displacements are considered to be negative numbers. So this counterclockwise displacements are considered to be positive. So delta theta will be positive, and a clockwise displacement will be negative, with the angular displacement delta theta less than 0. All right, the other point that I wanted to make here is this one. Each point on a rigid body experiences the same angular displacement during the same amount of time. How so? Let's look at these 2 points, and it looks like this angle might be 30 or 40 degrees of the angular displacement between the initial and final points that point on the rim was at. Well, let's look at a point halfway between the center of the CD and ask what its, actually it would be more over here to be halfway. So how far, what's its angular displacement during the same amount of time? Well, it moves through the same angle. This radius line moves through the same angle for this point halfway out as it does for this point all the way out. So the angle between here and here is the same as the angle between here and here is the same as between these 2 points here. So the take-home message here is that all points on a rigid body will experience the same angular displacement in the same amount of time as, well, they all experience the same angular displacement as any other point on it. And you say, well, what about this point right here? If we're looking at the same time interval from initial to final, this guy will come from here to there, and he'll move through that same angle that any other point does. I think I've made my point. So state the arc length equation. This is a mathematical relationship, but I didn't ever actually remember it very well until I learned it in physics. And so if you've learned it before and you already know it, that's great, but I'm going to teach it to you here. We'll need to use this over and over again in this section. So we're talking about the arc length. The arc length is the distance around a circular path. So it's not the straight line distance, but the arc. So it's the distance around the edge of the crust on your apple pie, from here over to here. That's why we call it an arc length. It's not a straight line distance. And this distance, arc length distance, is related to the radius of the circle, called r, and the angle through which you have rotated. And the relationship between them is s equals r theta. So that's just the way I remember it. S equals r theta. S is the arc length, r is the radius, theta is the angle, and the arc length is measured in meters. So it's a distance as the along this arc. Radius is measured in meters, and the angle, for this equation to be valid, the angle must be measured in radians. So this is valid. This equation is valid only for angles measured in Let me do an example, and the example is to check this relationship for a full circle, one full revolution. So the idea here is this. I'm going to start here, and I'm going to go around a complete circle and come back to where I started. And I want to know, if this is the radius r of the circle, what this equation will tell me about that situation. In fact, it won't tell me anything. It'll tell me something I already know. Here's the idea. The arc length, in this case, is the distance from here's the distance from my starting point to the ending point along this arc. Well, in this case, for a whole circle, it's the distance between this point all the way around here, how far I have to travel to go all the way around that circle. Well, what's that distance? And you say, well, isn't that the circumference of the circle? And I say, yes. So in this case, the arc length is the circumference of the circle, which is, as you might recall, 2 pi times the radius. So we're going to plug that into here, 2 pi times r in for s. That gives me this equation here. Then r and theta just come along for the ride. So what does this equation tell me? Well, magically, 2 pi, magically, I'm sorry, the r's cancel. You can divide through by r, and that gives you theta equaling 2 pi. So that's why I told you that this equation doesn't tell you anything you didn't know already, which is that a full circle means an angular displacement of 2 pi. So, big deal. But this confirms that this equation only works for angles measured in radians. And okay. Let's do an example. Synchronous satellites orbit at a radius of 4.23 times 10 to the 7 meters. So that's this radius here. If their angular separation is 2 degrees, then find the arc length between them. So these satellites are way out there. It's 40 million meters from the center of the Earth. And we want to know what the arc length distance is between those two. Well, we can find the arc length from this formula. We know the angle, so we know the radius. That's 4.23 times 10 to the 7 meters. Here's the angle measured in degrees, 2 degrees. And then, like we said before, in order to use this equation, we've got to have theta measured in radians. So we're going to convert this 2 degrees into radians by multiplying by the conversion factor that we mentioned before. The degrees will cancel, and there's 2 pi radians and 360 degrees, and that will give us an answer in radians for the angle theta. Plug all those numbers, this number times these numbers, divided by that number, and you get this answer. Now, a word about units here when it comes to applying the arc length formula and many other formulas in this chapter. You might have said, well, hang on, Dr. Edwards, don't you have a radian unit right here, and shouldn't we be multiplying by radians? And I say yes and no. The radian is a unit that's not really a unit. It can pop in and pop out of equations without any damage whatsoever. It makes a lot more sense to think of this arc length distance as measured in meters than to have it measured in meters times radians. It's just really measured in meters. So this is one case where the radians will pop out of the equation after you put them in. There'll be other instances that we'll see where you need to insert them back in to the equation, but that's all legal. All right. So the other final thing about this is that arc length, the distance, even though the angle between them is only 2 degrees, and of course this is definitely exaggerated. That's not 2 degrees, that's more like 30 degrees. 2 degrees is going to look like something like that. Even though they're very, very close to each other in the sky. In fact, 2 degrees in the sky is about the width of two fingers. Let me put it toward you like that. Between my eye and there, these two fingers subtend an angle of about 2 degrees. Even so, the arc length distance for that very small angle is a pretty big number. It's 1,000,000 meters or so, 1,000 kilometers. All right, another example. The sun's diameter is about 4 times greater than the moon's diameter. The sun is about 400 times farther from the Earth than the moon. And that is an amazing coincidence, if coincidence it is, because this fact allows us to see a total solar eclipse. And just think about the scale here. This scale is not drawn properly. The moon's 400 times smaller than the sun. And so this moon is only shown maybe 1/3 of the size, or maybe half at the most, of the sun. But you have to imagine this moon being 1/400th the size of the sun. That moon is just going to be just the tiniest little dot. And its distance is also 400 times smaller than the distance to the sun. But that amazing coincidence, if coincidence it is, allows you to see a total solar eclipse. So show how that's true. The angle subtended is the word that's used. The angle subtended by the sun is this theta sub sun. That means if you look at the top of the sun and the bottom of the sun, and you take those two lines into your eye, what's the angle between those two lines? And we can calculate that angle subtended by the sun and relate it to the distance to the sun, r, and the diameter of the sun, well, S is essentially the arc length. So the idea here is that arc length is comparable to the diameter of the sun. Really, it'll be an arc length like that. But this angle is so small that that arc length can effectively be treated as a straight line and be considered as the diameter of the sun. And so we know that S, the arc length, is r theta. So if we apply that to this situation for the sun, the arc length is essentially the diameter of the sun. Well, actually, S sun equals the radius to the sun times the angle subtended by the sun. And we can solve that for a theta sub sun. So that's the angle subtended by the sun, is the diameter, essentially the diameter of the sun divided by the radius. And so that's this equation right here. Well, the diameter of the sun is 400 times the diameter of the moon. And the distance to the sun is 400 times the distance to the moon. And lo and behold, the 400s cancel, and we have the diameter of the moon divided by the distance to the moon. And that has to be equal to the angle subtended by the moon. So that says that this angle subtended by the moon is the same as the angle subtended by the sun. These two angles are the same. And that's the reason why you can get the moon right in front of the sun and cover up the disk of the sun. That's what happens at a total solar eclipse. This was a photograph taken by my brother-in-law's brother and on August 21st, 2017. Up in Idaho. For those of you that were able to witness that total solar eclipse, it was one of the most amazing, moving experiences of my life. What you see in this photograph is the moon. This is the black disk of the moon that's covering up the hot, fiery disk of the sun in the background, and outside around it, this light that you see here is called the corona. I took my telescope up to Idaho to see that eclipse, and we had a lot of family members and friends there. And during the totality of the eclipse, the corona of the sun has about the same brightness as a full moon. So it was like a dark, well, it was like a moonlit night during that period of time. And you could see the corona, and we actually looked at the corona through my unfiltered telescope, which was just such a thrill. Anyway, great experience. I hope some of you had a chance to see it, because it really was a memorable, amazing experience. But that's how angular distances relate to eclipses.